Hello, everyone. Welcome back. For the first speaker of the session will be Milind Kulkarni from Purdue. And are the slides set up?
They just, oh, there we go.
Ah, okay. And he will talk about regularizing the irregular. Thank you very much for agreeing to talk at PLMW.
Well, thanks so much for having me. I hope everybody had a good lunch. I hope everybody's not too tired, either from jet lag or from a food coma. So I know my talk title is maybe a little bit vague about what, what we're going to do is kind of walk through what this means first. But let me actually start by saying that I'm really, really thankful for the opportunity to present at PLMW. I've been involved with PLMW for many years now. I've given talks here, I've organized it several times, and it's very near and dear to my heart. And one of the things that I've always liked about PLMW is that it is a mix of research and mentorship and fellowship. And what I'm hopeful that we can do in this talk is kind of get a mix of those things. So what I want this talk to be is both about some research ideas and some research perspectives, but also some perspectives on life and maybe how you might think about your own career. And to get started, when I talk about regularizing the irregular, what I'm actually talking about is abstraction. People often ask me, especially like freshmen that are coming in wondering what they want to do, like what makes a computer scientist a computer scientist? What makes computer scientists good at what they do? And I tell them that one of the things that makes us, our superpower as computer scientists is our ability to abstract, our ability to take complicated ideas, complicated objects, complicated systems, and add layers of abstraction on top of them that hide a lot of the messy details and give us a handle on how these systems work and what these systems do, so we can use just the pieces that matter in order to build much more complicated things. And we see this in computer systems all the time. The way that we deal with hardware is a story of abstraction. I'm actually in an electrical and computer engineering department, so I work with a lot of people that don't think about things at the level of abstraction that we do. They think about transistors. But we don't want to think about transistors in terms of transfer functions, right? We very quickly put layers of abstraction on top of that and think about transistors as switches. We don't think about switches. We put those switches together to create logic gates. We don't just think about logic gates. We put those logic gates together to create integrated circuits and to create ISAs and all the different things that we layer on top of billions of transistors so that we can actually take this insanely complex system and reason about it in a tractable way. And we do the same thing in software, right? We take assembly language and we then abstract that away into high-level languages. And many times these days, we don't even really think about high-level languages. We think about complex libraries that we put together to create more complicated programs. So this process of taking complicated systems and layering abstractions on top of them, hiding all of the messy details so that we can focus on what's important, is our superpower as computer scientists. And this is the thing that I think we all develop over time, and I think especially as good researchers we develop it. We think about how to generalize from a lot of examples of things in order to create useful abstractions. Once we have those abstractions, we think about how to specialize those abstractions to particular use cases, to particular hardware, to particular scenarios to make them work as well as possible. And then, maybe most importantly as a research community, we think about when it's important to throw away those abstractions and start over. Okay? And my take on this in general is that abstractions are what let us kind of sand off the rough edges of objects of interest, of things that we care about, so that we now deal with the spherical cow that physicists like to talk about, and we can think about these things in a much cleaner way, right? They let us regularize things that might seem irregular. And so today's talk is both a little bit about research and a little bit about mentorship. And really, I want to think about how regularizing the irregular, how building these abstractions provides perspective actually on my own life and my own work. And I want to think about both the advantages and the disadvantages. I want to think about times that hiding the details unlocks new ideas and lets us do new things that we never thought we could do before. But I also want to think about times that hiding those details and this power of abstraction actually obscures more than it reveals and can actually create problems. So we'll do these things kind of in turn. But where I want to start is what I do for research. So I work on the compiler side of compilers and programming languages. And in particular, I work on optimizing compilers. This was a thing that at PLDI was all in vogue back in the 80s and 90s, and it's kind of died out, although there's still a lot of people that, like me, that do optimizing compilers. And when I think about optimizing compilers, I think about two broad categories of compiler transformations. Okay? The first one is the one that I think a lot of people are familiar with, which are transformations that remove redundant or unnecessary or expensive computations. Opportunities to take a program and say, wait a second, you're doing more work than you really need to, so I can remove that unnecessary work in various ways, right? So if you've ever taken a compilers class, how many people have taken a compilers class? Great. So you know about common subexpression elimination, right? I do an addition, and I do a plus 3 2 times, and so I can remove that unnecessary addition and replace it with a simple move. Program gets faster. Great. We know about dead code elimination, right? I've got some computation that computes a value for x that immediately gets overwritten, so I don't need to compute that value of x anymore. I can remove that unnecessary computation. Code gets faster. These are sort of classic compiler transformations that if you open the Dragon book, you'll see tons and tons of these, right? The kinds of transformations that I work with and that I think about look a little bit different. These are transformations that reschedule computations. They do not remove any computations. They do not eliminate redundancy. There's no dead code. There are no common subexpressions. Instead, these transformations are about taking a set of instructions that you want to execute and executing them differently. So for example, here I have a really simple doubly nested loop that computes a vector outer product. It just multiplies two vectors by each other and gives you back a matrix. And loop interchange, one of the most basic scheduling transformations you can do, just changes the order of the I and the j loops. It doesn't do anything else. All it does is instead of putting the I loop on the outside and the j loop on the inside, it switches it, puts the j loop on the outside and the I loop on the inside. And if your experience of compiler transformations is those basic scalar transformations from the Dragon book, you might think to yourself, why would I ever do this? What good does this do? This literally seems like it does nothing. It's exactly the same instructions, just happening in a different order, right? Why does this help at all? Why would I do a scheduling transformation? And this is one of those times that the abstractions actually obscure details that turn out to be really important. Because when we think about instructions executing on a processor, we're thinking about instructions that get compiled down to assembly language, that get compiled down to machine code using an ISA. And an ISA, an instruction set architecture, obscures all of the details of the microarchitecture that actually goes into the processor that is executing those instructions. Right? An ISA does not tell you anything. Well, to some extent, does not tell you anything about the register files that are on your chip. You have a certain number of architected registers, but in reality, there are dozens and an order of magnitude more registers actually on your chip that get used when instructions execute. Your ISA doesn't tell you anything about multiple functional units, the ability to execute multiple operations in parallel through instruction-level parallelism. Your ISA, the abstraction that we use when we program a chip, doesn't tell us anything about caches, the fast memory that holds recently accessed data that allows us to do computations faster. Right? All of these details of the actual microarchitecture, all the rough edges that we sanded off when we put this abstraction in place, hide the complexity that actually affects how our program behaves. Okay? And in particular, it affects, when you change the order that instructions execute in, it affects how your program interacts with these hidden features and changes the performance of your code. So let me give you an example of this using loop tiling, one of the classic compiler transformations. So rescheduling operations can often make a program take better advantage of the caches that are in your system. And the key idea here is that what a cache is doing for you is it's holding recently used data so that the next time you access that data, you can access it faster. So instead of it taking hundreds of cycles to access a location in memory, it might only take 2 or 3 cycles to access a particular piece of data. So your goal is to take multiple accesses to the same location in memory and make them happen close together in time so that the data that you want is already in cache. So let's take our simple vector outer product example. And this is one of those learning opportunities here. Here's the way that a compiler writer might actually think about this code. From the perspective of drag and book style optimizations, this piece of code is actually very simple because there's really just this one little computation, right? One line of C code that's happening inside this loop. But in reality, and this is the key, in reality, when I execute this code, that one line of C code executes n squared times, right? Once for each possible value of I and j. So as a compiler writer thinking about instruction schedules, I don't want to think about it as one piece of code or one instruction. I actually want to think about it as all n squared instructions using this abstraction that we call an iteration space. So each one of these little dots here represents one particular time that we execute that line of code. A of ij is equal to x of I times y of j, once for each value of I and j. Okay? And I've drawn some arrows here to show you what the instruction schedule looks like. So I execute I0, J0 first, and then I0, J1, and so on. When I organize my code in this way, the particular instructions that I execute happen in that order. OK, so let's take a look at the two particular instances, one when I is 0 and j is 0, and one when I is 1 and j is 1. Okay? Each of those instances happens to access the same location in y. They both happen to access y0. Okay, so these are two separate instructions that happen at two different points in time that access the same location in memory. This is an opportunity to take advantage of your cache. This is an opportunity to say, hey, I've accessed a piece of data. Now I'm accessing it again. Wouldn't it be great if y0 was still in cache? So that instead of taking hundreds of cycles to access it, it only takes a few cycles to access it. How do we reason about that? Well, the way a compiler writer might reason about it is as follows. Let me look at those two accesses to y of 0 and ask how many other pieces of data I access in between the two times that I access y0. Okay, so between I0, J0 and I1, J0, how many other parts of y do I touch before I come back and touch y0 again? Okay? This is a notion called reuse distance. And it turns out the answer is all of it. From the time I access y0 to the next time I access y0, if you kind of stare at this code a little bit, tilt your head if it helps, you'll see that you access all of y. Now, when n is 4, maybe this doesn't make that big of a difference, but if y is a large vector, then you've accessed a tremendous amount of data potentially between one access to y and the next access to y, which means that you wind up kicking y0 out of cache. By the time you come around and access y0 again, it's no longer in cache. You get a cache miss. Your performance sucks. So what we do is we apply a transformation called loop tiling, which basically restructures the code to look like this. Now, from the perspective of classic scalar optimizations, this looks really crazy. Not only did I not remove any redundant instructions, I actually added instructions, right? This piece of code with 3 loops here executes more instructions than the original code does. But the reason this helps is if I think about the order in which I execute the instructions, and I think about the order in which this particular piece of code gets executed. I get a new schedule. Don't worry too much about exactly how it happens. It looks like this. Okay? It basically walks through 2 values of j entirely and then walks through the next 2 values of j and the next 2 values of j and so on. Okay, this is a transformation called loop tiling. And I can ask my question again, how much of y do I touch between accesses to y0? So I touch y0. How long does it take before I come back and touch y0 again? Well, now I only touch 2 total elements of y. So y0 is going to be in cache the next time I come around and see it. So even though I've actually executed more instructions, even though this piece of code is more complicated, if you actually apply this transformation, the eventual code runs significantly faster. Because instead of getting lots of cache misses every time you access elements of y, you get cache hits every time you access elements of y. Right? You can get orders of magnitude speed up by doing these kinds of transformations. And to me, this is an interesting example of how the abstraction that we love as computer scientists can actually hide important details. Right? We have this abstraction of how programs execute, where we think about the instructions that are executing in terms of just this ISA. And from the perspective of that abstraction, doing this transformation shouldn't make a difference, or in fact should make the code slower because you're doing more work. But in reality, everything runs faster. Abstractions can hide important details. Okay? So this is the first lesson. And what is interesting to me is that abstractions don't just hide important details when you're talking about computer science. Abstractions can hide important details when you're talking about people also. How many people have heard of imposter syndrome? Okay, so imposter syndrome, for those of you that have not heard of it, is this idea that everybody out there is better than you. Right, that's a gloss on what imposter syndrome means. But one way to think about it is you get into a room and you think everybody here is smarter than me. They're all more successful than me. They know more than I am. And I don't belong here. Okay. Now my take is that one of the sources, not the only source, but one of the sources of imposter syndrome is that when we interact with other people, we interact with them in terms of abstractions. Right. We look at the spherical cow version of them instead of all the messy details. So let me talk about my own abstraction and my own personal journey, right? If you were to look at my career from the outside, you would say, one, this all seems kind of preordained, and two, this all seems pretty good, right? I am one of those examples of how being an academic is heritable. Both my parents have PhDs. My dad is a college professor. He just retired this year. So of course, I'm going to become a college professor. I went and I started my PhD at Cornell. And so time is going along and success seems pretty good. I'm at a top department doing computer science research. Can publish lots of papers. I got a job at Purdue. I've been there for 16 years now, doing hopefully fantastic research, getting lots of funding, and being very successful. If you look from the outside, you might get that sense that, hey, this is exactly the path that you would expect a successful academic to take, right? Right down to the fact that his parents were academics. So let me tell you what's actually happening under the hood. So I did start my PhD at Cornell, right? And I certainly was hoping that I was going to publish lots of papers. But actually, I published no papers in my first 4 years as a graduate student. Research was not going well. And honestly, I didn't think I was going to do academia, right? I was like, I don't think research was for me. It didn't seem like it was, like I was really struggling with it. I didn't have great ideas. I didn't really know what I was doing. And I was getting ready to just kind of get some sort of degree and go off to industry. Things turned around. I was able to publish some papers, and then I went on the job market. And from the outside, you're like, okay, you got a job at Purdue. Great. Top department, things are going well. What this hides is the fact that actually I was on the job market in 2008, 2009. And now I know a lot of the people in this room are maybe a little bit young to remember, but that was an epically bad time to be on the job market, right? This was in the throes of the great financial crisis. Everything collapsed. Nobody was hiring. I actually got incredibly lucky to even interview at Purdue, right? And Purdue was the only academic job offer I had. As an aside, and you can come talk to me after the talk about this, the fact that I was able to interview at Purdue is actually an example of why it's so important to build a good network. And that's the only reason I was able to get the job. So I got to Purdue. Things seem okay. I'm going to do hopefully fantastic research and get lots of funding. But in reality, my first 2 years at Purdue, I got no grants funded. I submitted a dozen different grant proposals. Not a single one got funded. And so this is, I think, one of those situations where from the outside, the abstractions that we use to interact with each other can obscure a lot. Somebody would look at me, potentially, and say, oh, yeah, these are the kind of people that I'm not, right? And this becomes a source of things like imposter syndrome. But actually, if you peek under the hood, there were a lot of challenges. It really didn't go very well. In fact, I was on the other end, on the other side of imposter syndrome for a very long time. But one of the things that I did do after I finally got a cool idea while I was at Purdue was I decided to stop writing grants about little incremental things, small ideas, and instead to pursue a particular crazy idea that I had. Now, a particular crazy idea comes back to thinking about compiler transformations, and in particular, scheduling transformations. Because those scheduling transformations that I showed you earlier, right? This loop tiling, loop interchange, things like that. Most scheduling transformations that people had done in the past focused on what are called regular programs, programs that deal with loops, programs that deal with arrays, programs that deal with matrices, the kinds of things that you see in linear algebra, right? The kinds of things that you see in scientific computing. These kinds of programs are characterized by predictable data access patterns and predictable computation, the kinds of things that compilers can get a handle on because you can predict what's going to happen, and a compiler can therefore restructure the computation in order to get better performance. And there's a good reason that people focused on those kinds of programs, right? These are the kinds of programs that exist in scientific computing because when you solve systems of differential equations, you wind up with big matrices that you have to do linear algebra over. When you have stencil codes, you wind up with big matrices that you're doing computations over. When you're doing image processing, you've got big two-dimensional arrays that you're doing computations over, right? Regular programs, programs that deal with matrices and arrays and loops are everywhere, and that's what compilers had historically focused on. But not all computations are regular. Not all programs deal with loops and matrices and arrays. Lots of domains that still need high performance are irregular. They don't deal with well-structured data and well-structured accesses. Things like n-body simulations, things like data mining codes over irregular data, things like ray tracing. These programs are characterized by much more complex data, data that is not necessarily represented in arrays and matrices, but instead use pointer-based data structures. They use trees and graphs and lists. And because they use these trees and graphs and lists and they use these very data-dependent structures, their access patterns are much harder to predict. They're very unpredictable. And so the question that I wanted to answer, and the crazy idea that I had was, what if we think about these irregular programs at the right level of abstraction? What if we sand off the rough edges and think about them in a different way? Can I do those same kinds of scheduling transformations, loop interchange, loop tiling, stuff like that, on programs that look like this? So really quickly, to give you an example of what one of these programs look like, this is another one of the fun kind of learning pieces here. Let's think about a really simple data mining algorithm. It's called two-point correlation. The idea here is I've got a bunch of data points in some data set, so like n data points, and I've got some query point p. And this is a very simple query that I want to run. I want to know how many points from the data set are within this radius r of my query point p. Right? This is an example of an n-body computation, because the naive approach here is that what I'm going to do is I'm going to take all n points in my data set, all those gold points, and compare them with the gray point, and just do a distance computation. Right? This works, but it's slow. When you run these kinds of programs, you're often running them over millions or even billions of points. And so you wind up doing this big n-squared computation. Right? Every point is getting compared to every other point in order to compute this correlation. And it's extremely slow. But it turns out there's a better approach that people use where you use spatial acceleration data structures, in this case something called a KD tree, that lets you compute the result much faster. So the original n-body code looks like this. For every point in the data set, I just compute whether that point is close to my query point, p, and if it is, I just increase my count. But instead what I'm going to do is I'm going to build this tree structure that basically captures spatially where points are in this space. Okay, so what does this look like? In order to decide whether my query point p is, whether a particular, In order to decide which points in the data set are within R of p, here's what I do. I start at the top of the tree, and then I kind of work my way down the tree, and each part of the tree is a different subspace, and I just ask whether that subspace intersects that circle. And if the answer is no, then I know ahead of time, I know immediately that none of the data points in that subspace could possibly be in the circle, so I don't need to look at the rest of the points. So I can kind of work my way through my tree, right, until I get down to leaves, and when I get to the leaf of a tree, I do the actual direct distance computation. Okay? So I'm going to basically build this tree structure over my data points and walk over the tree in order to compute this correlation. And what I wind up with is a piece of code that looks like this. It's a recursive piece of code instead of a simple loop over all my data points. I walk recursively over the tree, right, doing a simple tree walk. And at each step, I ask whether or not I'm supposed to keep walking down the tree. Okay? Now, this has some good points and some bad points. The good point is that this is way faster It takes what used to be an order n operation. I compare p to every point of the data set, and it turns it into a log n operation. I'm basically just walking through the tree, and many times I can just prune big chunks of the tree off. The downside is it's not a loop anymore. It's a recursive code that's working over this tree data structure, so this pointer-based data structure, and it's very dynamic. What part of the tree I touch is completely data dependent. So I have these two different versions of my program. I've got in the regular world a simple loop over every point, and in the irregular world I have this recursive tree structure. And of course, in reality, I'm doing this for every point in the data set. So in the regular world, I say for p in points, then for n in the data set, I do this distance computation. In the irregular world, I recursively traverse the tree once for every point. Okay. When I look in the regular world, what I see is that this n-body code actually is really nicely structured. It actually just has two loops, exactly like we saw in that outer product example. Right? It's two nested loops, and I can do all of the same kinds of transformations that I would do before. I could do tiling and fusion and interchange, all the different things that I wanted to do, and I can make this code run really fast. But in the irregular world, I don't have two loops. I have this ugly mess, this recursive pointer chasing program. Right? So here was the idea. How do I deal with this irregularity? How do I deal with the fact that I'm doing this crazy pointer chasing? I'm just going to ignore it. I'm going to pretend it doesn't exist. In reality, what this pointer chasing code is doing is it's just deciding what part of the tree I'm supposed to touch while I'm processing this point. Right? So I'm basically taking a point and I'm deciding what nodes in the tree this point is going to visit. That's all this code is doing. So I'm going to hide it away. I'm going to build an abstraction that I'm just going to call magic. And the point of this abstraction is just to decide which nodes in the tree I'm going to visit. Okay? All of the pointer chasing, all the data dependence is hidden inside this magic function. I've abstracted away all the complexity. And why did I do that? Well, now I have a doubly nested loop. I've got, for p in points, right, for each query point, I'm going to ask this magic function what part of the tree I want to touch. It gives me back a set of nodes. I walk over those nodes, and I'm done. Right? The magic function has hidden away all the complexity. I've abstracted away all the complexity, and it's given me a doubly nested loop. And from this vantage point, the irregular world looks just like the regular world. Once I sand away the complexity, all of the same tricks and tips and transformations that I used to be able to do on loops, I can port them over to the irregular world. What do I mean by that? Well, this is what our code might look like. Okay. So imagine I'm thinking about node C in this tree for two different points. And I ask myself, between two accesses to node C, how much of the tree do I visit? And in the original program, between two accesses to node C, I basically walk over the entire tree. Point A, or this point, touches node C and then walks over the rest of the tree before I can come back and touch node C again. So thinking back to our regular world, this is really bad. It basically means I've touched the entire tree every single time. And what that means is that most of the tree doesn't stay in cache, and I get lots and lots of cache misses. But I have a doubly nested loop. I can do loop interchange. Rather than saying for p in points and then for n in nodes, what if I swap the loops and say for n in nodes and then for p in points, which might seem like a weird thing to do. Let me tell you what this is actually doing. It basically says take node A, the first node in the tree, and have every point interact with node A. Then go to node B, the second node in the tree, and have every point interact with node B. Go to node C and have every point interact with node C. So rather than taking a point and making it walk over the entire tree, we take a node of the tree and have it interact with all the points it's supposed to interact with. And it turns out once you do this, now everybody deals with node A, and then they don't need to worry about node A anymore. Everybody deals with node B, then they don't have to worry about node B anymore. And so the tree actually stays in cache through the entire traversal. I don't get any cache misses anymore in my tree. And we did this in a bunch of different settings, and it turns out that when you do this kind of transformation, you get a 3x speedup just from better cache performance in the tree. But you can do more. Once you structure the code like this, it turns out this piece of code can be vectorized very easily. The original code really couldn't. The new code can be vectorized. You get a 3x speedup. The new code, because it can be vectorized, actually maps very cleanly to GPUs. The original code was a lot of pointer chasing recursive code, doesn't work very well on GPUs. This code fits really well on GPUs if you structure it this way. You get a 100x speedup. So by sanding off all of the rough edges and creating this little magic function, it sure seems like I got a free win, right? I was able to restructure my code. I was able to do all the transformations that I wanted and get much better performance. Where did this go? OK. So the question that you might be asking is, well, OK, this is all well and good, but you're hiding the ball, right? You took all of that complexity and you stuffed it into this magic function, and now what's happening, right? What's really going on in this code? Well, it turns out that that magic function is not that magic. Once you have this idea in your head that you want the code to work in this other way, you want to go node by node through the tree instead of point by point through the data set. Once you have that in your head, it turns out that sorry, I want to make this point more clearly. Making the code work the other way instead requires adding about 4 extra lines of code. Right? It's simple enough that it fits on one slide. Right? Once you use this insight to restructure your code, actually generating the code is not so bad. And then this code gets you a 3x speedup. Basically, what's happening is that instead of recursing with one point at a time, I take a block of points and have the block of points walk through the tree. Now, I'm still hiding some details. Right? So there's some details left to make this all work really well. So there's details like, how can you tell that your transformation is safe? Like, I restructured my code. It's no longer operating in the same order. How do I know that that's actually a valid thing to do? It turns out that's really hard, but you can figure it out. There's details like, how do you generate this code efficiently? There's lots of different ways to implement a particular schedule. And some ways of implementing that schedule actually slow your code down. So you need to do this carefully and think through it. How do you tune your transformations? How do you know how big the tiles should be? How do you know how big the block should be? These are all questions that people asked and answered over decades of research in the world of regular programs, over decades of research in the world of loops and arrays and matrices. And by having these ideas and thinking about irregular programs at the right level of abstraction, you realize that there's those same questions to ask and hopefully answer in this other world. And there's lots more to do. There's lots of messy details that aren't automated yet. There's more complex code generation you need to do. There's new hardware features like ray tracing cores on modern GPUs that actually might let you hardware accelerate irregular programs. And ultimately, the goal is, can you create compilers that fully generalize both regular and irregular transformations? So a few takeaways. Compilers are able to restructure programs in order to take advantage of hardware capabilities. They can take advantage of multi-cores and big caches and vector units and GPUs and all of the complex hardware that the ISCA folks have come up with over decades. Right? Irregular algorithms, pointer-based data structures, data-dependent accesses, they're difficult to optimize, but there's still lots of opportunities out there for performance improvements. And if you think about your problems at the right level of abstraction, then you get a handle on what you might be able to do in order to make them run better. Right? It makes it easier to reason about the transformations, and it gives you a lot of insight into what you should do to make your code run faster. But the final takeaway is to be careful. Sometimes those messy details, whether it's in life or in research, really do matter. And so it's important to pay attention to those too. I want to close by saying that really the actual secret of my success is a huge number of amazing students that I've worked with over the last 15 years. And without them, none of this would have worked. Questions?
All right, questions?
So first, thank you for the nice talk. And at the beginning of the talk, you said the imposter syndrome originates from the abstraction people made to describe themselves, and this abstraction hide away the messy things behind behind one person, and expose the happy and great things of one person. And I wonder if is there any benefits of abstractions for people and yeah.
So I do want to say, I want to be careful here. One, I'm not a psychologist. My wife is a psychologist, but I'm not. And so my take on imposter syndrome is not that this is the only source of imposter syndrome, but I do think that one of the things that contributes to imposter syndrome is that when we look at other people, we only see the clean exterior instead of understanding all of the complexities that go on under the hood. And so things that look like they're doing really well, maybe they're struggling also. And when we don't see that, that can contribute to our own imposter syndrome. I will say that I think that one of the useful things that abstraction gives us is that when interacting with people, is that it also, in the same way that abstractions in computer science give us a clean interface that we can use to access, to deal with a pretty complex system, abstractions give us ways of interacting with people without having to kind of rethink how we interact with each person based on their own internal complexities. Whether that's good or bad for you, I don't know. But it does mean that, for example, you're here at PLDI, you're about to go and meet a bunch of different people, right? You have an abstraction of the people that are here, which is that they are researchers that are interested in programming languages, and that gives you an easy hook and an easy way to interact with them and interface with them without having to relearn that about them every time. And so those are situations where I think it is useful.
Thank you.
So you mentioned that you entered the job market right after the 2008 financial crisis, which sounds awful. What would you say you've learned from that experience that you could give to young researchers entering the job market while a bunch of research funding is currently being gutted? Which, I mean, is maybe hard to answer because we're all terrified, right?
Yeah, no, I am terrified for you guys as well, and honestly for my community, right? Like so much of our community is dependent on this constant refreshing and this constant bringing in of new blood, and anything that disrupts that is really scary. And I don't know, I'm trying to figure out how to answer this without being like a huge downer. Because one of the things that actually did happen in the wake of the financial crisis that I think was really useful, at least in the US, is a bunch of programs were put in place to keep people in the academic pipeline by offering postdocs and things like that. But if there's kind of a uniform drop in research funding, that kind of thing becomes harder. I would say the advice that I would give is to be open to opportunities that you might not have considered before. To some extent, that's kind of what happened with me winding up at Purdue. I'm not in a CS department, I'm in an ECE department. Now I happen to be in what I think of as a really great ECE department. I'm biased, but it's one where there's lots of opportunity for very computer sciencey work to happen. But I think there's a lot of people that would just dismiss out of hand the idea of going to an ECE department. If anybody here is from the University of Michigan, you'll know that there's some really great formal methods people that are in like the aero department at the University of Michigan. There are opportunities for the kinds of things that we do in a lot of places, and I think everybody should be open to those opportunities.
It's really good to hear you say that as someone from the University of Michigan, so that's great.
So John Batiste, right, is in their aero department. I didn't know that before.
Thank you for the presentation. So you said that in the first years of your PhD, you didn't get any published paper.
I was miserable.
So what I wanted to know is if you have any advice on paper rejection and how to handle that.
Well, step one is to find an incredibly patient advisor, because my advisor put up with a lot from me, and a real lack of, I'll be honest, a lack of productivity. I spent a lot of time trying to figure out what I wanted to work on. It wasn't even really paper rejections. It was, I didn't really know what the right problem was and what I should be trying to do. And I had a very patient advisor that helped me work through that. Honestly, what I would say is that my sense of this is that a lot of us, I think, get really hung up on this idea that if I don't get a paper my first year as a PhD student, or if I don't get that first paper in, like I'm just like, that is going to set me off on the wrong path. And I just want to tell everybody that that's not true, right? I think earlier Chiron was saying that like one of the most important things that a researcher can have is perseverance. And honestly, that's the hardest thing about getting into research in the first place, is dealing with the fact that the things you're trying might not always work. And so having a supportive advisor, but honestly having a community that's also there to tell you that no, it's okay, like this happens. And if you believe in your ideas and you keep working at things, like you'll get there, is really important. Papers are going to get rejected. It sucks, but it's normal.
Thank you.
Yeah, first of all, thank you so much for a great talk. Do you have any advice on how do you go about balancing abstractions and details? Because both of them seems important.
They're both really important. Like I said, right, one of the most important things that we do as computer scientists is to understand when to look under the hood and when to throw away an abstraction because it's not working for us anymore. I don't have any great advice. For me, it always feels like it's just an experience thing. Like you try something and you get a taste for like whether it feels like it's going to work or not. I do think that you don't want to be too fast to throw away abstractions that exist. Like you should have a really good reason for doing it, because the abstractions that do exist often do exist for a reason. I will say, and I tell this to undergrads all the time, like one of the reasons that I really like thinking about computing not just at the level of algorithms and things like that, but really starting from electrons and building up, sort of the computer engineering approach to computing, if you will, is that you learn how all of the abstractions are built, right? So don't throw away abstractions too quickly, but you guys should take it upon yourselves to understand how those abstractions are built. Why were those abstractions designed the way they were designed? What actually is going on under the hood? Not because you want to get rid of them, but because that gets you the understanding that you need to know when it's time to move on. So don't throw away abstractions too quickly, but definitely take the time to understand what's going on under the hood.
All right, let us thank Milind again for the great talk.